All right, so we're going to talk about truss, which we kind of did last week, but in a more comprehensive term. So, yeah, so I talked about, beam resists the load by bending, but truss is only through axial force. What does that mean? Anyway, so let's read that because I wrote it in. Truss is a structure composed of slender members. As you can see, they're pretty slender. And they are called two-force members. What it means is the force that each of these cores in the truss is experiencing is either compression or tension only. They don't experience bending stress, right? So, and that's the fundamental difference between the truss and the beam. So these two force members are joined together at their endpoints. Joints are modeled by smooth pin connections. So these joints, in reality, it looks more like this one on the top called A, like with these bolts or, gusset plate and all that. But, to diagrammatically represent that joint, you show this pin joint, which I showed last week. As these things, right? So basically, this pin joint means it's completely free to rotate. It doesn't move X or Y, but it has zero resistance for rotation, right? So those are the joints for the trusses. Yeah, anyway, and members are either under tension or compression. Right? Yeah, so anyway, so these are kind of various different kinds of trusses, some of which we are going to analyze and dictate what internal forces in each members are. But anyway, these are kind of diagrammatically shown. You can see these two force members, and all these round nose are pin joints, meaning it does have zero resistance for rotation. It just kind of like puts two together, right? Anyway, so let's talk about simple trusses. So these are called simple trusses. Anyway, so this is kind of what I think I explained using these physical models last week. So let's look at the left one. So yeah, so if you imagine this kind of like quadrilateral panel with 4 members and 4 joints, if you apply a load at point B, as seen in blue, it's not hard to imagine that it's gonna do this, and it's going to deform, and yeah, it's going to completely lose its shape and it's unstable, right? However, if you have 3 bars and 3 joints, like it's shown on B, basically a triangle with 3 pin joints, you can also easily imagine that it does not deform at all, and that's purely through a geometry and number of members and number of joints, and that's basically what determines whether the truss is stable or not stable. It has nothing to do with the nature of the joint, because the nature of the joints are exactly the same, right? They're pin joints that cannot resist any rotation. So some of which I would ask you to actually go through physically. So it's not only the triangles that can be called simple trusses. You can achieve a larger rigid truss by adding 2 members and 1 joint each time. So this is adding this green one, 2 bars and 1 point. And you can keep going. And so, for example, this is an example of that simple. So it's not, so you can imagine keep adding a triangle, 2 bars and 1 joints linearly, and you end up with a truss that kind of looks like this. But it's not you can also achieve a simple truss, not just with triangles, right? So this one is also a simple truss, which I'll show you the process later, but start with triangles, add 2 and 1 point, 2 and 1 point, 2 and 1 point, and 2 and 1 point. So these are kind of called simple truss. Simple truss is basically you start with the triangles and you keep adding 2 bars and one node. So this is kind of showing the step by step. You're starting with a triangle, 3 members and 3 joints, right? And you add 2 members here and 1 joint. As you can see, I didn't change the color, which I should have. 2 members and 1 joint, which is this one and 1 joint. 2 members and 1 joint, 9 and 6, and so it's kind of a simple math, right? At the end it's going to be 11 and 7, and that's showing sort of the similar one as the one from last page. So basically you can keep doing this math and you can actually arrive at this generalized formula, which is number of members equal 2 times number of joints and minus 3. If the number of members and number of joints satisfies this equation, it's basically a simple truss. So far so good. More kind of generalized, you can actually, so this is about the simple truss, but I mean, you can find a video or text about how to prove these formula, which I'm not necessarily interested in doing. I think what you need to know is actually all of the trusses that we will be analyzing would satisfy this equation at the top, which is a determinate truss, which is, there's this term called statically determinate or indeterminate. There's strict definition to that, which I'm not going to go into, but basically if you think of it, so determinate structure is something that you can clearly get the answer using only the statics. Basically whatever we're doing, what we are able to provide an answer for what forces in each member is only if the trusses are determinate. When it's indeterminate, it's basically there are multiple solutions for that problem, and you cannot actually solve that by only using statics, which we won't get into because for us we were only dealing with determinate truss. What's kind of important is this unstable one. So if for example, which we're gonna kind of explore, so we won't have to get into details, but so basically know that pretty much all of the trusses that we're gonna see in the problem and we will be analyzing is determinate. If it's members and joints and reactions I will get to, but if if m is less than 2j minus r, that means it's unstable, meaning that truss could actually deform under certain loading, right? So which is something that we don't want, right? So that's the kind of truss that you would never want to design, right? Because basically how the trusses are able to support the structure is completely depending on the geometric property of the truss and stability of the truss. So if the truss is unstable and it's going to do that, you can't really support the structure, so that's not good. So just know that the unstable is bad, and make sure that m is not less than 2j minus r. If it's more than 2j minus r, it means we cannot solve it, but it could be still stable. Anyway, so this is just showing the example. You can check that later. So reactions. So how do we know how many reactions there are and why are there 3 reactions on this truss? That's because I will show you in the next image too, but in all of our problems we So there are two support points for this truss, right? But we are showing one of the joint as a pin joint, which is, oh, actually I'll get it to later. And the other joint is, you see this round thing, it's called the roller joint. So I will explain what they are. And if you go to page 2 of Beer's book, you can see this definition of these different support points and number of reactions, but we are really looking at this roller and pin joint. So roller joint it's a little bit abstract concept, but what it means is basically, because it's on the roller, right? So it's a roller joint, so it's on the roller. So if you basically push it in X direction, right, it's gonna move. So it has zero resistance to this sort of horizontal movement, right? So if it tries to move, it's gonna move, right? But it has resistance to vertical loading. So if you try to push it, it's gonna provide reaction. The next point is slightly kind of tricky to grasp, but it also has reaction towards this way. So it won't squish, but you also cannot lift it off, which is weird to think about, but that's how the roller joint is defined, right? So it moves this way, but it cannot move up or down. Does that make sense? So therefore, that's the reason why there is only one reaction for roller joint, because there can only be this direction of reaction and there's no reaction this way. Pin joint, however, it's let's say this is a ground and this is your support point, and I can actually push this way, right? And how it's shown here, the more intuitive way is if I'm pushing it this way, right? The applied force is this way, and your reaction at the joint must be this opposite diagonal, right? So it looks like one reaction, but it's a convention to divide that diagonal reaction into two horizontal and vertical components. So if you have this diagonal, right, it actually resisting this force in vertical direction and horizontal direction, and that's why it's defined to have two reactions. So that's actually kind of, if it's the pin joint, right, we would basically assume, even if there's only a vertical applied load, we would still assume that there are two reactions because it's capable of providing two reactions. So that's why we would consider this truss to have a three reactions, which is typical for pretty much all the problems that we're dealing with. So that's just kind of so you know why there are three reactions. So yeah, so in this case, this is a pin joint, so it has this reaction and that reaction. So for example, if you've had a load that went this way, right? If the loading is diagonal, it's gonna have a component. Should have drawn this in, but let's say typically you load the truss at all these joints, right? So, and typically there are vertical forces, but let's say if there was a diagonal applied load here, then that's gonna have a component, horizontal component and vertical component, right? And that joint on the right, which is a roller joint, has zero capacity to resist a horizontal load, so it's gotta be resisted by this guy. So if there's that much horizontal component in applied loading, then there's gotta be a equivalent magnitude of reactions in opposite sense at that pin joint. That makes sense? Alright, so that's just to cover the basics. understanding. So the truss problem that I would be giving you in Rhino file would typically look like this. And because in almost all the problems we are just going to be looking at the vertical loading, so you probably will forget about this horizontal reaction, but if you pay attention, it's always, the left side is always drawn with a pin joint, which is this triangular symbol, and the right side is always drawn with a roller joint, which is this round symbol. So that's just kind of cover the basic. Now, so I'm actually kind of curious how much time it takes, and this is up until 11:45, right? So not sure how long it takes, but basically what I want you to do is I laser cut all these pieces for you, and then there are these joints. There's absolutely not enough for one person, so I gotta ask you to do it in group of 3 or per table, right? Whoever in the back find 2 other people and form a group of 3, right? And then first of all, right, like it might be not hard to imagine, but like something like that, it's slightly, well, that's actually not hard to imagine. But for example, like, let's see. For example, when I first did it, I found it difficult to comprehend that, okay, so that's not gonna move. That's not gonna move. And that's not gonna move either, right? That's not gonna move, but that's not gonna move either, and it takes a little time to kind of like sink in, like, because if you just look at that part, it looks slightly unstable, but it's actually stable because of all these guys around it. So it's not just how it looks locally, but it's also has to do with the relation to whatever was before. So anyway, I think in using these parts, I want you to kind of start with a triangle and try to do this, like adding 2 and 1 joints, 2 and 1 joints, and 2 and 1 joints, and etc., etc. And count the number of members and joints and see if it satisfies the equation below, and compare with the behavior of your truss. So in other words, maybe try to also make something that it's not stable, meaning that something that's you can kind of deform, and see how that fits in this equation. That's one. And then once that's done, we can, maybe we could try to use some of these as a guideline, and is that gonna move or is that stable, and that kind of stuff. So I think, all I'm trying to do is to kind of have you have some sort of a intuitive grasp of what this thing is. So there are just a lot of these things, so it's kind of hard to. And how these are, the long one is actually. So actually the geometry you can make is pretty limited, because the long one, it's basically a. Alright, so I'll show you. So basically short one is, how long is it? I forgot. It's like short one is, if the length of the short one is L, right? The length of the long one is like basically √2. Anyway, so long one is like this diagonal in the square, and the short ones make up the square. So you're sort of limited to this squarish geometry, but I think you can still kind of explore these different options and see what's stable and what's unstable. Does that make sense? So this is kind of a first trial for me too. And so how many did I cut? I think I cut 300 of these and 500 of these. So, and they are, let's say, 12 groups. So I think I don't know, grab a handful and start. And somehow he can do
Nothing so much for you.